Hello and welcome everybody to this brief tutorial on how to use the stellar wind and irradiance module, otherwise known as the acronym SWIM. And this is code that we developed last week at the third Eddy Cross-Disciplinary Symposium in Vail, Colorado, and I created it with some collaborators, and this is currently a Jupyter notebook being hosted in the cloud by 2i2c. And essentially what this code is meant to do is read in files from the mussels database, which was a survey of over 20 M and K dwarf stars, and read in a spectra from one of those stars that you pick, then rebin the spectra to a particular model, be that a stellar wind model or a climate model, and that could be a one-dimensional or three-dimensional climate or exoplanet model. And then you scale that spectra on that new wavelength grid to the particular irradiance that a planet in that star system receives. So if there's 5 planets or just 2 planets in that star system, then you can pick one of those planets and the final spectra will be ready, available for you, saved out from the code onto the wavelength grid you want at the right irradiance that the planet receives. So what I'm going to do is run through it now quickly and show you how fast it is just to create a spectra of your choosing. So here we're having the mussels data type selection, and there's 4 options, and I'm going to click variable adaptive resolution. And then you get a choice of the stars from the mussels database. So you can see all the stars labeled GJ here, and then we have the HD stars, and of course everyone's favorite 7-planet system, TRAPPIST-1. I'm going to select here GJ667c. And then what happens here is I've read in that file, so you can see it here has downloaded all the data in the file, and now we are ready to plot the spectrum. And here we have on a wavelength grid of nanometers the spectrum of GJ667c, and the flux density is plotted on the y-axis, and this is the flux density, I believe, that Hubble saw when it made the observations. So this flux density is very low. It's not currently scaled to the planets. So I'm going to run through some more cells here, and then we come to the climate model list. So at the moment, I have implemented this for Wacom, CAM, and Rocky 3D, and we also have a custom constant grid and a custom variable grid. I have listed other climate models that I know are used in the exoplanet community. However, I haven't implemented the grids for them, as I don't currently know the stellar input files that these models take. So if you do want to add them, please let me know and I will implement it, or you can, because it's on GitHub, pull the repository down yourself and make some edits to the code to use it however you want. So because I principally use CAM and Wacom, I'm just going to select Wacom here. And what that does is it reads in the solar file that Wacom uses, and then I'm going to plot the solar file next to the mussel spectra of GJ667c, and now I've scaled them so they both have the same irradiance of that the Earth receives, which is 1,360 watts per meter squared. And what you can see here is that the spectra are not on the same wavelength grid. The mussel spectra is a lot finer than the Wacom wavelength grid, the black grid here. Wacom also extends further into the infrared, and mussels extends further into towards the shorter wavelengths, X-rays down here. And then I'm going to read in the NASA Exoplanet Archive. So I'm only reading in the columns that I need, which include the planet name and the host name and the star's luminosity, and that's done now. And then I run this cell here, and I get all the planets that are around this particular star. And there are 5 planets here. I'm going to select the planet E. And this tells me that planet E is 0.213 AU away, and it has the star has a luminosity of 0.0137 times the luminosity of the sun, which means that GJ667CE receives 0.3 times the flux that is received by the Earth. And then finally, I do some more plots and rebinning. So I'm just going to run through some of these last cells here. And what that's doing now is it's showing me that I've rebinned to the Wacom wavelength grid. So the number of flux points and wavelength points in each array are exactly the same. And I've also scaled it so that we have an irradiance of 0.3 times the flux that the Earth receives. So this means that I can now spin up Wacom with this particular stellar spectral file and create a run. I basically choose the planetary properties of GJ667CE and begin that run, because the spectra is now scaled exactly how I want it to be, exactly based on the information that is currently in the most up-to-date row in the NASA exoplanet archive. The nice thing about this is at the end it saves out the file, so you can just copy and paste that into whatever directory you need to use it in your climate model. And maybe you want to create another spectra, I can go back to this row here and pick planet G. Again, it tells me the information. Planet G receives even less radiation than the previous planet did. And I run through this again. What that does is it's going to save out the file and it's going to plot the spectra again on that same grid that I showed here. But this time the irradiance is less, so this blue line is actually slightly under the black curve now, and we have another spectra. Now, this was taking me a few hours to do previously, and now it's taking me 5 minutes to create several different spectra scaled to each planet in the system. So I hope this is useful to the community out there. Perhaps there was a tool that existed like this before, I haven't seen it. And hopefully this can be a really nice, simple, easy to use tool for the community to very quickly create and modify spectra for different planets so that we can get on with doing the science. Thank you very much for listening, and please get in touch if you have any questions, criticisms or ideas. I'd love to hear them. Thank you.